Hello, everyone. This weekend, we're just going to go over kind of what we did. So, first things first, the output of kind of what we did, it was collisions. So, as you can see, that we're using mouse, we've tracked mouse movement now, and we are going to, when the mouse hovers over, it becomes true. When the mouse is not over it, it's false. How we did that was we'll explain, and then we'll also explain how we got mouse movement to work. So let's first go to input. What we added was a mouse move, a static mouse move function in our input class, which takes the event, and then we just set the variable equal to the client X and the client Y. And then inside of engines, we now listen for mouse move through input.mousemove. So now whenever we want to reference mouse move with like a triangle component, we just now can call input.mousemove to get the position of our mouse. One thing to note is that we will always need to have a if input.mouse position is a valid issue, because if we take a quick look at this, read it all there. If I reload, so you see how there is no mouse variable or value existing because my mouse is off the window. Even over here, it's off the window. Once it enters the canvas, then it shall start working. So that's a key thing. Whenever you reference mouse position, you have to check it first. But now what we do is we just print collisions.inCollision input.mouse position this.game object. Now, when we actually look at what this is doing, if we go to collisions, the first thing we can dig that up is that we're doing is overlapping vertices. What this is we have basically a point and an array of values inside of our vertices. And what we want to do is we want to see if the point is in between the min and max of vertices. So for example, we look at over here, we say 3 is our point, for example, and then we have an array of 5, 6, 4, 13, and 12. The way we do that is we check the min, which in this case is 4, and the max, 13, and we see if 3 falls in between those two. Since 3 doesn't, it's false. And we can see that when we check our console log. Yep, it says it's false. Next is our is overlap. With this, what we do is we have a point and then we have some vertices. Or no, is overlap point and vertices direction would be our next one. What we do is we project the point into the direction into some direction, and then we also project each vertex in said direction, and then we check if. Then we call the is overlap position vertices to check if the point projected in said direction is in between the vertices projected in that direction. And then we just return the collision dot is overlap. Finally, we do is overlap. Is overlap, we have a point and vertices, and what we do is we get vertice 1 and vertice 2, or the next index of vertices, and at the n-1 index, we loop over back to 0. Then what we do is we get the edge vertex itself, or vector itself, and then we normalize it so it's at a range from 0 to 1, and then we get the the orthogonal or the 90-degree the vector in the 90-degree from that one we did. So the way we can actually look at this is Desmos. What we do is say we have a y equals x. What we do is we normalize the 2 points, so we get a point at 1, 1. We minus it from 0.00. So now we only have a point from 1, 1 minus 0, 0. Let's actually do 1, 1 as well. All right, let's do 2, 2, just to make it a little bit more obvious. 1, 1, and 0, 0. So we have a point 2, 0, and we subtract 1, 1, or 0, 0, and then we get this vector this way. What we then do is we make it orthogonal, which means that we just switch the y and the x in direction-wise. So y would equal negative x. Now that is the direction we're going to project in. So when we do is overlap vertex, when we have the point, the vertices, and then the direction, what we do is now we project in this y equals negative x direction whatever the vertices are, which in this case is 2, 2, and 0, 0 with some point. Finally, we call, and if it returns false, that means we are not in collision. If all of them are, if the result is false, we return false because that means that we are not in collision because there is a gap between the lines where you can fit through it, basically. But if all of them return false, then we return, or if the result returns true on all of them, then that means we have to return true because that means that there's no possible line we can make to separate or distinct between the two, the point and then the vertice. And now within collision, we have a point and then we just have some sort of game object. What we do is we have constant we get the polygon component, and then for every point in polygon dot points, we do transform points dot push. And then since our points are just local space, we need to put them into world space, or model space into world space. What we need to do is we need to do transform points dot push, and then we have to add the transform dot position relative to allow us to shift to where the actual in-world position it will be. Then what we do is we call then return is collision overlap points and transform points, which then does the previous statements. The final thing that we shall review is Vector2. So you have a constructor. We already had all this, but the next thing we added was an add, which is just this dot x plus other dot x, and this dot y plus other dot y, minus, which is just the subtraction version of add, orthogonal. You switch the y and the x value and make the y negative. Dot is this dot x times other dot x plus this times y dot y times other dot y, and magnitude is a getter, and it's just the square root um, of this dot x to the power of 2 plus this dot y to the power of 2. Normalize, if the magnitude is 0, what we want to do is return 0, 0 because that means that it is just a 0, 0 vector 2. Otherwise, we return this dot x divided by the magnitude, and then this dot y times divided by the magnitude in a new vector 2, and then clone just returns a new vector 2. So now, kind of piecing it together, when we check if our mouse position is valid. If it is, then we call the collision.inCollision with our input.mouse position and then our game object. Um, the final thing that is somewhat of value is our different types of collision. We have our static collisions, um, where it is a static and a player, and this is where the player collides with a static object. And basically what happens is it just stops the movement of the player. There's also like a player and player, which is where physics is applied equally. And then there's also a third one where it's pretty much a collider and player. And that is just um, where this is where we're doing like overlapping detection. One way to get more information on this is if you go to Home, you go to be course notes. Would it be communication? No. Nope, I guess we don't have that. But just remember that there's three types of collisions. One where it is like player and player, where physics is applied to both. One is physics is applied to one side, and then one is physics is applied to neither side. Some examples could be like you hit a wall. This is where like physics is applied on one side, the player side. Another example could be you hit another player, and that means that physics is applied on both sides. And then the final one is like you reach the end zone or like the final zone, and this slash the checkpoint. And this is where um, you detect if a collision happens, but no physics happens. Those are the three main ways that collisions happen. Those are the three kind of examples you could have. Because when you hit a wall, you want the player to stop physically and collide with that wall. But if you hit another player, obviously, both of those will have unique physics when with like collisions. Like one example is like the cue ball hitting the 8-ball, and they both react in their own ways. And then if you reach the final zone / checkpoint, what you do is you have to detect if a collision happens, but no physics shall happen with it. Hope this helps. If you have any questions, comments, or concerns, you can always email me or talk to me after class.